Welcome to ChemFire, where we talk about topics related to chemistry, physical science, and earth science. Today, our topic is the kinetic molecular theory of gases. This theory discusses the movement of gases at the molecular level. And there are 5 assumptions. Let's take a look. Assumption number 1 is that individual gas molecules vary in their size and their mass. Assumption number 2 is that these gas particles are moving at random. There are many different gas molecules and they move at different speeds. Some move slowly, some move more quickly. And as they're moving, they may collide with each other or with the sides of their container. When they collide with either one another or the sides of the container, this can change their direction and or their speed. A third assumption of the kinetic molecular theory of gases is that these individual gas molecules are separated by great distances. There's a lot of just empty space between individual gas molecules. A fourth assumption of the kinetic molecular theory of gases is that there are no intermolecular forces of attraction or repulsion between them. These particles may momentarily collide, but there's no other forces keeping them together, unlike a liquid or a solid. And a fifth assumption of the kinetic molecular theory of gases is that collisions of these gas molecules are elastic. What that means is that there's no net loss of energy when these individual gas molecules collide with one another. Let me give you an example. Here we have the all-familiar Newton's cradle. And we know that when I go ahead and I raise one of these balls and let it go, it's going to hit another ball. And it's going to transfer energy to that ball, and it's just going to keep going back and forth. This is a close model to what we mean when we say gas molecules are elastic. When they hit one another or they collide with one another, they're just going to transfer energy, like this. The kinetic molecular theory of gases gives us a basis for describing the physical properties of gases. First, gases have a very low density. Why would gases have such a low density? Yes, think about the kinetic molecular theory of gases. One of the assumptions was that there is a lot of empty space between individual gas molecules. All this empty space is going to give gases a much lower density. A familiar physical characteristic of gases is the ability to compress. Think of it when you're trying to put air into a soccer ball or your bicycle tire. Why does gas have this physical property? Think about the molecular theory of gases. There's a lot of empty space, and so gases are able to be compressed or squeezed into a much smaller area. A third physical property of gases is that gases are able to expand to fill whatever container they're put into. What assumption of the kinetic molecular theory would account for the ability of gases to expand? That is correct. Gas molecules are in constant motion, and so when allowed to fill a larger area, they will do that. They will expand. Fourth physical property of gases is that gases are able to diffuse. That is, they're able to reach equal concentration in a given volume. What assumption of the kinetic molecular theory of gases accounts for this diffusion? That is right, that the gas molecules are in constant motion allows for this diffusion of gases. This is why we're able to smell a student behind us that just passed gas. Lastly, gases are permeable. That means that more than one gas can intermingle with one another. This allows us to smell things at the same time. In the morning, your mom might be sizzling bacon on the stove, also brewing coffee, and you can smell both of these things. Or, the example that I gave before, there's that student that passed gas behind you, and Mrs. DeBoer pulls out the Febreze, and you're able to smell the pleasant smell of the Febreze along with the gas. Why is that? What assumption of the kinetic molecular theory accounts for gases' ability to be permeable or to intermix? That's right. There's actually 2 assumptions. One is that the gas is constantly moving, and secondly, all this empty space allows other gas molecules to fill in. Let's talk about the relationship between the pressure, the volume, and the temperature of gases. In this chart, we have the relationship between pressure, temperature, and volume on gases. Look with me at case 1. In case 1, we're holding the temperature of that gas constant. And while we're holding the temperature of that gas constant, we're going to increase the pressure. What's going to happen to the volume of that gas? That's right, the volume of that gas is going to decrease. This is an example of an inverse relationship. When we are increasing one aspect and it causes a different aspect to decrease, that's an inverse or indirect relationship. Look with me to case 2. In case 2, we are going to keep the pressure constant. Now, if we want to keep the pressure constant, but we increase the temperature, what's going to happen to volume? When we increase the temperature, it's going to cause those molecules of gases to begin moving more rapidly. Okay? And as they move more rapidly, there's going to be more collisions with one another and with the sides of the container. We don't want to increase pressure. We want to keep pressure constant. So to keep pressure constant, the volume of the container is also going to have to increase. That's an example of a direct relationship, where one increases, the other increases as well. And so that would be true is if we decrease temperature, and we still want to keep the pressure constant, when we decrease temperature, the kinetic energy of those gas molecules is going to slow down. And so that means the volume of our container is going to have to decrease as well if we want to keep pressure constant. And lastly, look at case 3 with me. In this situation, we want to keep the volume constant. So if we increase the pressure, what is going to happen to temperature? That's right, temperature is also going to increase. Okay? So as we increase the pressure, there's going to be more collisions with those molecules, and so there's going to be an increase in temperature. If we decrease the temperature, gas molecules are going to slow down, and so there are going to be less collisions, and that will also decrease the pressure. That's another example of a direct relationship. When one decreases, the other decreases. Thank you for taking the time to view this short video on the kinetic molecular theory of gases. I hope that you now understand the 5 assumptions of the kinetic molecular theory and how those assumptions form the basis for our understanding of the property of gases.